All right, in this video we're going to take a look at section 5.3, which is on properties of logarithms. The first topic in the notes is the change of base formula. I assume this is because the textbook covers it in this order, but I would like to skip past this material for the moment and talk about the other properties of logarithms, and then we'll come back to this, and I think it'll make more sense if we cover it later. So let's go ahead and skip past that for right now. And let's talk about these other properties of logarithms. I mentioned this previously in class, that logarithms are exponents. So remember we talked about this in 5.2. If I want to find log base 2 of 8, I ask myself the question, how many powers of 2 does it take to equal 8? And the answer to that question, in this case 3, is what the logarithm is equal to. So it's a terrible arrow. Right, there we go. It's equal to 3, right? So the logarithm equals the exponent. Logarithms are exponents. And so their properties behave like the properties of exponents. And so what I mean by this, and this is kind of the short explanation for why logarithms behave the way they do. If we look at property number 1, the product property, we have log base A of u times v. We're multiplying here, right? We're multiplying the u and the v together inside of that logarithm. What do we do with exponents when we're multiplying? So for example, if you have x to the second power times x to the fifth power, what do we do with the exponents in that case? We add the exponents together, right? 2 plus 5 gives me 7. And that's how I get the new exponent. That is why we are adding these logarithms together. So if you're multiplying the u and the v inside of the single logarithm, it turns out you can split those up into separate logarithms, but you will add those individual logarithms together because those logarithms are representing the exponents associated with u and v. And if you're multiplying u and v together, you would add those exponents, so those logarithms get added together. Right? So it's multiplication inside the single logarithm, but when we split it up, we add the individual logarithms together. But again, if you can think of it in terms of how exponents behave, it makes perfect sense. When you're multiplying two things together with the same base, you add the exponents. Therefore, we're going to add the logarithms. Because again, just for repetition, logarithms are exponents. They behave as exponents behave. Same thing for property number 2. If you're dividing, what do you do with exponents in that case? So we have like x to the fifth power divided by x to the second power. We will subtract, okay, that was a terrible color choice, but we subtract those exponents. 5 minus 2 gives me 3, and that becomes my new exponent. So when we're dividing, we subtract exponents. So that's why this property up here makes sense, right? Here we are dividing, so yeah, I guess I'll just say divide, and when we split those up into separate logarithms, we will subtract those logarithms because that's what we would do with the exponents. And again, logarithms are exponents. All right. One of my favorite properties of logarithms is the last one, which is log base A of u to the n power. And what this property is telling us we can do is we can take the exponent inside the logarithm and multiply it down in front of the logarithm. So now we get n times log base A of u. So I'm sorry, I'm kind of making a mess on the notes here with these examples that I'm doing, these sort of side examples that aren't directly in the notes. Why does that property work the way it does? It's the property of when you raise one power to another power, right? So x to the fifth power raised to the second power. What is that going to equal? Well, if we are raising one power to another power, we multiply those exponents together. And we get x to the 10th power. And that's what's happening in this example. So we have u to the power of n. So u itself has its own associated exponent. It's not written there, but there's an exponent that's associated with the u in terms of base a. And that's getting raised to the power of n. So we're putting another exponent on top of the exponent that's associated with the u. So what do you do in that case? You multiply n times that exponent that's associated with the u. The logarithm is representing that exponent associated with the u. And so that is going to get multiplied by the new exponent, which is n. And so we end up getting n times log base a of u, right? Because again, you're basically multiplying those exponents together. N is your one exponent, and then log base a of u is the other exponent. And when you have one power raised to another power, you want to multiply those exponents together. So that's why we're multiplying those two things together. All right, there's this extra column over here for the natural logarithm, but as I mentioned previously in class, it's silly to rewrite the same rules out. I think it is. Now, I hope that doesn't come across as insulting, but it's a logarithm. I know it's not spelled out log, but natural log is also a logarithm, so of course it will have all the same properties that the regular logarithms have. So, all right, so I didn't leave myself any room to do these examples. And these directions are kind of weird. It's more like a puzzle trying to figure out how to do this. We want to rewrite each of these logarithms in terms of natural log of 2 and natural log of 3. So we want to get only 2's and 3's. So we have to rearrange the numbers we're given. We have to rewrite them so that all we have are 2 and 3's in our logarithm, and then apply the properties of logarithms as I wouldn't say as necessary, but that's not really what I want to say, as the opportunity avails itself. So like apply the properties of logarithms whenever you can, right? All right. Well, I really didn't leave myself any room here. So here's what I'm going to do. I haven't done this in a while. Let's use a shape, and then we will make it like that. And then I'm just going to, okay, it's supposed to be not that color. Oh, okay, it's right here. Okay. Okay, wow. Okay, that's a square. I should do a rectangle instead. All right. And so magically I create some more space. Now I've covered over the directions there, but again, you have your notes printed out. Don't cover up your directions on your notes. You should leave those there because you might want to read those later. All right, so let's look at example A down here. We have natural log of 6. We want 2's and 3's, so I think this is a pretty obvious one. You want to rewrite 6 as 2 times 3. Okay. And now, because we're rewriting it as two things multiplied together, property number 1 is available now, right? We are in this situation. We have log base e, in this case, natural log, of 2 times 3, right? We have two things being multiplied together. This property tells me I can split that one logarithm up into 2 separate logarithms, so the 2 and the 3 will get to go inside of their own logarithms, but we will add those logarithms together because that's what you do with exponents when you're multiplying. You add the exponents together, so the logarithms will get added together. So what we're going to end up with here is natural log of 2 and natural log of 3, right? These will each go inside of their own logarithms, and we will add those logarithms together. All right. Any questions? That's a habit I have when I'm in the classroom. Of course, on a video, you can't ask me questions, so sorry, that's kind of embarrassing for me to say that. All right, moving on is what I should say. Let's look at part B. I didn't leave myself any room to do this. I guess I'll just keep moving down here. Let's look at B right here, and then I'll just do these examples even further down. And I'm sorry if you have trouble finding space for it in your notes. We're doing this one here. We have the natural log of 2 over 27. Again, we want just 2's and 3's. That's what the directions tell us. We already have the 2 there, so that's fine. We can let the 2 slide. But the 27, we can't leave that as a 27. I only want 2's and 3's. So how can I rewrite 27 with a 3? Now you might be thinking, it's 9 times 3, but we don't want the 9 either, right? We just want only 3s and only 2s. The 9 could be broken down again to 3 and 3, right? So you can actually rewrite 27 as 3 times 3 times 3, or a better way of writing that would be 3 to the third power. Right? So that's what I would recommend doing with the 27. Rewrite it as 3 to the third power. Now we're dividing here, so I'm going to break these apart, put the 2 in its own logarithm, put the 27, which is 3 to the third power, in its own logarithm. But because we're dividing, these logarithms should be subtracted, because that's what you would do with exponents in the case where you're dividing. You would want to subtract the exponents, so therefore I will subtract these logarithms. So I guess maybe I could diagram that up here a little bit better too. We're multiplying here, therefore we will want to add those logarithms together. Now in this current example, there's one more property of logarithms we can apply, and it's the property where you have an exponent inside the logarithm. You can bring that exponent down in front of just that logarithm. So it doesn't go down in front of the whole problem. It just goes multiplied in front of the logarithm that it's a part of. And so my final answer here would be natural log of 2 minus 3 natural log of 3. And so that's writing it in terms of log base 2, or not log base 2. That's rewriting the problem in terms of natural log of 2 and natural log of 3. All right, so I almost said any questions again, just out of habit. All right, let's look at this next example. This one doesn't have the same directions. We're not going for 2s and 3s in this case. We are being asked to expand each logarithmic expression. So we just want to split it up into as many separate logarithms as we can, spill out as much as we possibly can from each logarithm, just take up as much space as we possibly can with this problem. That's kind of the goal here. So the rules that we were introduced to at the top of the page were set up where if you have 2 things being multiplied together, you can split those 2 things up into 2 separate logarithms. But that can be chained together and applied to multiple things. So if you have 5 different things being multiplied together, you can split those up into 5 separate logarithms. Right? So technically, if we're applying the rule literally, we would have to do 2 things at a time, but we can just kind of skip to the end, skip to the punchline, and say everything gets split up into separate logarithms. That includes the numbers, right? So we have 5, we have x, we have y, all of those get separated into separate logarithms. So what we're going to end up with is log base 4 of 5. Sorry, it's a funny looking 5. Let's try that again. We'll have log base 4, so the base stays the same, of x, and we'll have log base 4 of y. Now, what do I want to do with all of these logarithms? I want to add them together, right? Because everything here is being multiplied, right? This is multiplication, and this is multiplication. So if it's all multiplication inside the single logarithm, then when I split it up, I want to add all those individual logarithms together, right? So because we're multiplying, we're going to add these logarithms together, right? Because that's what you would do with exponents in the case where you're multiplying. You add the exponents together, therefore you add the logarithms together. I'll stop saying that eventually, but I just want to make sure the point gets across. Now you might think I've made a mistake here because there's something I left out. You might say, wait a minute, Mr. Fallen, it's log base 4 of x to the third power. You're absolutely right. There should be a power of 3 here with the x, but I didn't write it there because, again, skipping to the punchline, what am I ultimately going to do with that power of 3? I'm going to write it down in front of that logarithm using the power rule that we had at the top of the page. So any exponents that you have inside of your logarithms, you want to bring those down in front of those individual logarithms. So that 3 is going to end up here. So I don't normally bother writing the 3 at the top right there, because I know what I'm going to do with that power of 3. I'm going to put it in front of the logarithm instead. And I just kind of save that for the end of the process. So as you can see, so this is the answer. And what I like to point out is, we're kind of taking a shortcut here. And there's really no steps to these problems. So, on the exam, I'm very particular about show your work. But for this type of problem, you can do it without there being any steps. You can just kind of skip to the punchline and just have the answer written out on the very next line if you know how to break it apart, interpret it, and interpret it the right way, as we've done here. So this is my final answer. And again, no, there's not really any work required there. You just have to know how to parse it, how to translate it into these multiple logarithms. And you can just kind of do it all at once instead of step by step. All right, we have one more example I almost forgot about. This one right here. So let me skip down a little bit more. It's going to go off the screen. So let's see, 3x minus 5 and 7. All right, 3x minus 5 and 7. All right. So I'm going to do the same thing here. Whenever they throw a radical into the logarithm, what you're going to want to, I'm talking funny, what you will want to do with that is rewrite it as an exponent. And then as an exponent, you can bring that number in front of the logarithm. So you never want to leave radicals as radicals in these problems. You want to rewrite those radicals in exponential form, and then as an exponent, you can use that power rule to bring it outside the logarithm. Right? So the first thing I would recommend doing here is rewriting that square root as a 1/2 power. All right, so I'm going to put parentheses around the 3x minus 5, because that's what was in the square root originally, and I'm rewriting the square root as a 1/2 power. All right. Now we're going to break these logarithms apart. The 3x minus 5 will go in its own logarithm. The 7 will go inside of its own logarithm. Because we're dividing here, we will want to subtract those logarithms. Now you might say, wait a minute, the previous problem you said even the numbers go inside of their separate logarithms, so should I put the 3? Should it be more like this? Natural log of 3, natural log of x, natural log of 5, right? Shouldn't I split those up into separate logarithms? And the answer is no, you can't do that. Because if you look at the rules closely, what kind of logarithms can we break apart into separate logarithms? Logarithms where there's multiplication or division, and that's it. You cannot split up a logarithm if you are adding or subtracting with the elements that are inside of that logarithm, right? So because we have a division, we can split that division up into separate logarithms. That's why we're getting 2 here. But that's as far as we can go because that subtraction, 3x minus 5, prevents us from breaking it apart any further. I could only do that if it was 3x times 5, then I could split it apart. Or if it was 3x divided by 5, then I could do more with that. But because I'm subtracting, it's a dead end. I can't break that logarithm apart any further. So no, we don't want to do that. So it's kind of a trick question, I believe, why that's in here. What we can do is take that power of 1/2 and put it in front of that logarithm, and we are done. All right, so it's breaking that logarithm apart as much as can be done. All right, let's look at the next page. This time we want to go in the reverse direction. We want to take these individual logarithms, these separate logarithms, and rewrite them as a single logarithm. So condensing is a good descriptive term for that. So again, we're going to jump to the punchline. We're not going to do this step by step because you can. And if you look at examples, you'll find a lot of examples will do this. They'll say, okay, well first you bring the numbers inside the logarithm and then you combine logarithms together 2 at a time because that's how the rules are set up. But we can just kind of do all of it at once. My ultimate end goal here is to have a single logarithm. So I'm just going to start off by writing that. Do you guys remember what the base of this logarithm is? Right? If it's not written there, it's base 10. Right? So this is log base 10. And then everything else around and associated with these two logarithms, I'm just going to fold it back up into a single logarithm. I'm going to repackage it so it all fits inside of just one logarithm. So I'm going to set up some big parentheses here because I have a lot of stuff to put in there. We are adding, so we're going in reverse, right? If you're adding the individual logarithms, that means you're adding the exponents together, and you would only be doing that if these things are being multiplied inside that single logarithm. So I'm going to take the x and the x minus 1, sorry, it's plus 1, excuse me, I don't know why I said minus 1, plus 1, and I'm going to multiply. I'm multiplying those together inside of that single logarithm. Now because there's two terms there, x plus 1, I'm going to throw some parentheses around that. But adding means I want to multiply those things together inside of the single logarithm. And then the numbers in front of those logarithms, when I bring those back inside the logarithms, they become exponents. Again, we're doing that rule in reverse, right? This rule right here works in this direction as well. You can take this that's in front of the logarithm, bring it back inside the logarithm, and it becomes an exponent on that thing inside of that single logarithm. So the 1/2 is going to become a power on the x. So I kind of got in my own way here with this arrow, so let's kind of erase that. Okay, and maybe redraw it up here a little bit higher. I'm really bad at drawing arrows for some reason. Okay, let's try that again. Oh, I'm still sorry, I don't know why it's bothering me so much today. Okay, so this is going to be, let's use a different color. 1/2 right here, right? A power of 1/2. Make sure you write it as an exponent, put it kind of higher up in the air. And then this power, or sorry, this number here, 3, which is in front of the logarithm with the x plus 1, that will be brought inside the logarithm as a power on just the x plus 1. And so we will have, let's try that again, we'll have a 3 here. Right? And that would be all you need to do with that. So you might think, oh, do I need to simplify? Not in this case. If it was simpler, I'd say, sure, go ahead and multiply it together. But x plus 1 to the 3rd power is going to be kind of a, complicated thing. And then remember, now maybe this would be worth doing, I didn't think about this, but a 1/2 power is a square root. So since we're condensing it, it wouldn't hurt to convert those fractional exponents back into radical form. Right? So it would look like this, but this is nothing that's worth simplifying. It's a mess, so we'll just leave it the way it is. Right? Now on WebAssign, I don't know which answer it's going to prefer, so it hopefully would accept either version of that. For part B, we'll do the same thing. We're going to condense these down to a single logarithm. It's a natural log, so I'll keep that the same. I'm planning to put everything inside of one logarithm. There's only 2 logarithms here, and we're subtracting those, which means I will want to divide, right? So again, going backwards, if you're subtracting your individual logarithms, you're subtracting your exponents. And you would only be subtracting exponents if the things are being divided inside the single logarithm. So since we're subtracting here, I don't know, maybe I don't need to write out the words, but I could do this maybe. Right. So this, and because we are subtracting, that's why I'm making this a division. Now, when you're dividing, it matters the order you divide in. So for multiplication, doesn't matter. 5 times 2 is the same as 2 times 5. So it really doesn't matter what order I put these in my logarithm because multiplication doesn't care. Division does care, right? 5 divided by 2 is different than 2 divided by 5. We get a different answer. So I got to make sure to divide these in the proper order. So what should go on top is the positive logarithm's content, right? So the x plus 2, this is the positive logarithm, so it should go on top. So I'm going to put x plus 2 on top. And then x, this is from the negative logarithm, so it should go in the denominator, right? So any content from a positive logarithm should be in the numerator. Any content from a negative logarithm should be in the denominator. That's the general principle, right? You're always dividing by what's in the negative logarithms, right? And then if there's any numbers outside the logarithm, those become exponents. So this 2 would be brought back inside of this logarithm. So it becomes an exponent on the x plus 2. So I need to go ahead and put some parentheses around it so I can raise it to the 2nd power. And I'm hoping that it would be okay just to leave it like that. Now this one you might consider multiplying this out because it's not too bad. X plus 2 times x plus 2. I'll leave that to you to work out the details, but you FOIL it, you get x squared plus 4x plus 4. So you can also write it like this, x squared plus 4x plus 4 over x. Right? But even that doesn't really simplify any further, so I'm not really sure if it's worthwhile to do that. Okay. Last one on this page, and then we're going to jump back to the first page to talk about the change of base formula. And I'm hoping I'll be able to kind of explain to you why that formula works the way it does. So this one has these like big brackets here. I guess what I would do with this is distribute the 1/3 into those brackets. I think that's going to work better. So we're going to have 1/3 log base 2 of x plus 1/3 log base 2 of x plus 1. So when you distribute it, that 1/3 doesn't get distributed into the logarithms, it just gets multiplied to each logarithm, right? I don't know if that made sense what I just said, but I'm not distributing it into, like, inside the logarithm. It will stay outside the logarithms. And since I'm adding two things together here, that 1/3 gets multiplied to both of those things, but outside the logarithm, not inside the logarithms, right? And then it's just what we did before, right? I'm going to write this as a single logarithm. The base stays the same. Because I'm adding, I'm going to multiply these two things together. So I'll have x times x plus 1. The number is outside the logarithm. Running out of different colors to use here. Become powers on those things. So we'll have x to the 1/3 power and x plus 1 to the 1/3 power. And that all goes inside of a single logarithm. So I think that should be sufficient. Maybe, I don't know if WebAssign cares about this, but we could write this as a cube root. So we'd have the cube root of x, right? Because it's a 1/2 power is a square root. A 1/3 power is a cube root. A 1/4 power is a 4th root. Right. This would also be a cube root. So this one's kind of interesting. And so maybe I should have left the 1/3 power outside the logarithms and did it a slightly different way, because these, if they're both the same radical, you can multiply those together into a single radical, which I think would be a little bit nicer than leaving it like that. So it would look like this. So any of these are equivalent. I don't know how picky WebAssign is about exactly the way your answer is formatted. If this was on an exam, I think I would just take any of these as answers to the problem. I don't. Yeah, I mean, like the first one, maybe, I don't know, I might like you to write the 1/3 power as a radical, but it's not in the directions, so I don't think I would count it against you if you left it like that. So any of these three would be fine on an exam. All right, let's go back to page 1 and talk about the change of base formula. This will go pretty quickly. So, fortunately, I hate that I had to sort of have this lecture be done outside of class, like on your own by watching a video, but this is actually probably the best section to do it with because it's a pretty short section. We're pretty much done. We have one more topic here, and hopefully easy enough to follow along with. But if you have any questions, please be sure to ask. Okay, so when I first started recording, I'm hopefully going to edit this part out because I changed my mind and kind of started over. Is the change of base formula is given by what you see here. I really like this one. Again, these are just kind of special cases for base 10 and for the natural log, but again, it works the same for those because they're logarithms as well. So this rule, the first one covers all of them. So there's no reason to memorize these separate formulas when the first formula covers those cases too. So you can change. So what's happening here is our logarithm is starting out in base A. And remember we talked about this in class. Some calculators, like my calculator, does not let me type in whatever base I want. So if I'm trying to find, for example, log base 4 of 25, this calculator doesn't do that. So I wouldn't be able to answer that question. I don't know what that's equal to, right? And I can't get my calculator to tell me either. However, we can change the base from base 4 to a base that my calculator can do, which would either be log base 10 or natural log. It can do both of those using this formula. So I'm going from base A to base B. So notice that both of these logarithms are base B. Right? This one's base A, and these two are base B. And there's a certain pattern that you follow here, which is the thing that's originally inside the logarithm, the x, the thing inside the original logarithm, stays in the logarithm on top. Right? And the base of the original logarithm goes inside the logarithm of the denominator, and the new base can be any base you want. That's what's kind of amazing about this formula, right? We could go to base 10, we could go to base 5. The pattern would stay the same whatever base you decide to go with, right? We're going to go with a base that we could do on our calculator. Now, why does it work like this? So the reason I wanted to do this last is to kind of explain why that formula works the way it does. And the explanation for that is a little bit ahead of where we are right now. We're going to talk about this stuff in 5.4, solving equations. But let's say I want to solve this equation here. We have 2 to the x power equals 7. In 5.1, we talked about that you cannot solve this by dividing by 2, right? If you divide by 2, the base stays the same, you subtract the exponents, you get 2 to the x minus 1 power. You can't get x by itself by dividing by 2. What we did in 5.1 is we changed the base of both of these so that they were the same. And that worked in 5.1 because the problems were set up for that to work. But here, that doesn't work. I can't rewrite 7 with a base of 2, right? 2 to what power? I don't know, right? It's not going to work out nice. So what we have to do with these instead, again, we're going to talk more about this on Wednesday when we cover 5.4. What we can do is we can apply a logarithm, right? Now, we have to choose what base to use. And you have two good choices here. You could choose to use the same base as your exponent, right? Because that's going to cancel it out. We did talk about this previously, right? If the bases are the same, they cancel each other out. If I do that to the left-hand side, I have to do the same thing to the right-hand side. So what ends up happening here is the base 2 logarithm cancels out the base of the exponent, the base 2 exponent, and we just get x equals log base 2 of 7. And that is a correct answer. However, I still don't know what the solution is, right? Because what is log base 2 of 7, right? It's just like log base 4 of 25. I don't know what that number is, right? If I told you I ran log base 2 of 7 miles today, you wouldn't really know how far I ran because that number doesn't really compute for us, right? But that is the solution. It's kind of a circular solution because remember, what does log base 2 of 7 represent? It's how many powers of 2 it takes to equal 7, right? Which of course is what I'm looking for, right? My equation is 2 to the x power equals 7. I'm trying to find how many powers of 2 does it take to equal 7. And my answer here is however many powers of 2 it takes to equal 7. So it doesn't really clear things up very well. What would be nice is if I could plug it into my calculator. So what I can do instead of using log base 2 is I could use, I'm running out of room here, I could use, so let's rewrite this equation. I don't know if that's enough room. Let's just slide down here actually, right? Let's rewrite the equation. But this time, let's use a base that I can plug into my calculator. I'll do log base 10. So I'll apply log base 10 to the left-hand side, log base 10 to the right-hand side. And what happens this time is the log does not cancel out the base of 2. It doesn't cancel it out. But we have this new property that we just learned today, which is that exponents inside the logarithm can be multiplied down in front of the logarithm. So it lets me bring the x from being stuck in the air, in the exponent, lets me bring it down to ground level where I could then get it by itself, right? So the x goes in front, we'll have log base 10 of 2 left over, equals log base 10 of 7. Now I can solve this for x. It's being multiplied by that log base 10 of 2. So to get the x by itself, I'll divide by log base 10 of 2. Right? And I get this answer, right? which I'm going to write up here. We get x equals, right, these cancel out. I get log base 10 of 7 over log base 10 of 2. And that is also a correct answer, which I can actually now plug into my calculator because it has a base that I can actually work with, right? So I get log base 10 of 7 divided by log base 10 of 2, and I get a decimal answer. I get 2.8074. So again, I just go 4 decimal places because that's just what I'm used to. And now I have some idea of how many powers of 2 it takes to equal 7. About 2.8. 2.8 powers of 2 will get you to 7, right? So that's kind of nice to be able to figure that out. And we'll talk more about that, like I said, in 5.4, but what I want to point out to you today is that this, let me use a different color here, this and this are equivalent. Right? These are the same. Right? Geez, I can't do arrows today. Okay, let's try that again. All right, there and there. Okay. They're the same. So log base 2 of 7 was a correct answer, but so was log base 10 of 7 over log base 10 of 2. Right? And the only difference there is it's a different base, right? That goes from base 2 to base 10, and notice it follows the exact same pattern, right? We have what's in the original logarithm stays in the logarithm on top. The base of the original logarithm goes in the logarithm of the denominator, and the new base happens to be base 10, but we could have chosen any base here, right? The base of this logarithm doesn't matter to solving the equation, right? I could have base 5 there, and all the rules still work the same. The x still gets multiplied down in front. I could divide that logarithm over, and I solve it that way, right? We chose base 10 because, again, we can use that in our calculator. So that's why the change of base formula looks the way it does. You don't need to really understand all that to use that formula, so let me just kind of demonstrate for you. For log base 4 of 25, I'll use that change of base formula. I'm going to change it to base 10. The 25 stays in the logarithm on top. The original base goes in the logarithm on the bottom, and now it's in base 10, which I can now plug into my calculator, and I can get a decimal answer, right? So I'm sorry, it's kind of messy there. We're going to have log base 10 of 25 divided by log base 10 of 4. Right, and we get 2.3219. Right, when you go to 4 decimal places, again, it's a run on decimal. I'm just stopping at 4. All right. So now, you know, I might have made some of you feel bad in class when I said, well, some of you might have calculators that let you type in the base of 4. And some of you won't. And maybe some of you who didn't have that might have felt left out or like, oh, maybe I need to buy a new calculator, which you don't need to do. Because now we have this formula so that now we're all on the same level, right? Everybody can calculate log base 4 of 25. Some of us will just be able to type it in directly. Others of us will have to do this slight change to change the base to base 10, and then we can plug it into our calculator. So that concludes section 5.3. Let me know if you have any questions, and I'll see you in class for 5.4.